Ohayou gozaimasu. Good morning and howdy from Temple, Texas. Hajimemashita. My name is June Wolf. I'm an associate research scientist and I work for Texas A&M AgriLife Research here at the Blackland Research Center in Temple, Texas. I've worked for Texas A&M since 1987 and I currently direct the Water Science Laboratory here at Blackland. My lab conducts basic research in water resource conservation and management, mainly through field monitoring, laboratory analysis, and environmental data assessment. I'm excited to speak to you today about the models that have been developed here at the Temple Lab that are used worldwide. My sincere thanks and gratitude go to Dr. Mori and Dr. Samora for inviting me to participate in today's symposium. I've known Dr. Mori and Dr. Samora since 2005, a few years, back when they worked at Shimane University in Matsui. Since then, we've collaborated on a number of projects and made more than a few visits, them to Texas and me to Japan. It's been a very good collaboration, and I look forward to many more projects and visits. I can't wait to come see you at Okayama University, and as you know, you are always welcome here in Texas. Before I speak to you about the Temple models, I'd like to tell you everyone a little bit about the Texas A&M system, the agency I work for, AgriLife Research, and a little bit about my water quality lab. Texas A&M University was established in 1876 as a land-grant university with a focus on agriculture and mechanical arts. Today, the Texas A&M system is one of the largest higher education systems in the United States. With a statewide network of 11 universities and 7 agencies, A&M system members educate more than 150,000 students each year and reach another 22 million people through its service programs. We have more than 26,000 faculty and staff, and the A&M system has a physical presence in 250 of the state's 254 counties and a programmatic presence in each county. System-wide, externally funded research expenditures exceed $990 million annually and significantly affect the state's economy. If you'd like more information about the Texas A&M system, please follow the link you see here in the slide. Texas A&M AgriLife Research is the agency that I work for. It's the state's leading public agency for research and development in agriculture, natural resources, and the life sciences. We have a statewide presence through A&M campuses, regional extension centers, and stations, and we provide solutions for today's challenges. The goals are to enhance competition and prosperity in agriculture, sustain healthy ecosystems, and conserve natural resources. As you can see, we have over 13 research and extension centers spread around the state, 10 research stations, a number of faculty and staff, and quite a few doctoral level scientists. AgriLife Research has collaborations with well over 30 nations worldwide. So I am very proud to be a member of Texas A&M AgriLife Research. In 1909, Texas agriculture suffered a major setback when an airborne fungus destroyed the cotton crop. This led to the establishment of the Blackland Research Center in 1912. The center has since been the site of continued agricultural research focusing on crop improvement, tillage strategies, and erosion prevention practices for the Blackland Prairie area of Central Texas. Blackland Research and Extension Center is part of Texas A&M AgriLife Research and the state research agency affiliated with the Texas A&M system. It is one of 13 off-campus research and extension centers that, along with Texas A&M University faculty, performs research and delivers education programs for the citizens of Texas to ensure a safe and affordable food supply, save and restore the environment, and strengthen the economy. A 12,000 square foot office building constructed in 2000 houses AgriLife scientists working at the center. Blackland Research and Extension Center shares research facilities with the Grassland Soil and Water Research Laboratory of the United States Department of Agricultural Research Service. VREC and ARS scientists have worked cooperatively together in Temple for over 80 years. Blackland Research and Extension Center research programs also include scientists from the U.S. Natural Resource Conservation Service. The synergism between Blackland and Grassland scientists is a principal reason for the success of the Temple Lab. Research programs from both agencies are closely linked, and scientists leverage shared resources and capitalize on the strengths of one another. I direct the Water Science Laboratory here at Blackland Research and Extension Center. My lab develops and applies new technologies to improve water management through fundamental and applied research. We use water quality and quantity measurements as surrogates to determine land condition, trends, and management effects. The photographs you see here on the slide show you the many different activities that the lab is involved with, from measuring stream flow for ecological reasons or flooding events to runoff from agricultural fields to sample collection and analysis in the lab. You see looking at sediments, nutrients, and bacteria. All of this information is used to help collect information for driving computer models. So now that I've introduced you to the Texas A&M system and told you a little bit about my lab, I'd like to speak to you about the Temple models and give you a few examples of how they're applied. Computer model development at Temple, Texas has a long history. Modeling research began in the mid-1960s with the development of single event models that served as building blocks for the comprehensive models of today. The focus of these early models was on surface water hydrology, rainfall excess, unit hydrographs, flood routing, that sort of thing, and sediment yields. The most popular models currently supported at Temple today include the Environmental Policy Integrated Climate Model, EPIC, the Agricultural Policy Environmental Extender, APEX, and the Soil and Water Assessment Tool, SWAT. Now, these are continuous models that operate on spatial scales ranging from individual fields all the way up to giant river basins. These models have been used worldwide in many projects dealing with soil and water resources and environmental management. So now I'd like to give you a little bit of rundown on each model and then give you some examples of how they can be applied. EPIC, the Environmental Policy Integrated Climate Model, was a plant growth model initially developed in the early 1980s to estimate soil productivity as affected by erosion. But since then, it's been extensively modified and expanded. Today, it's a process-based computer model that simulates the physical and chemical processes that occur in soil and water under agricultural management. This model can be divided into separate components describing weather, hydrology, erosion, nutrients, soil temperature, plant growth, plant environment control, tillage, and economic budgets. It's designed to simulate a field or farm or small watershed that's homogeneous with respect to climate, soil, land use, and topography. If you'd like more information about the EPIC model, theory and operator manuals are available at the link you see there at the bottom of the slide. APEX, or the Agricultural Policy Environmental Extender Model, was developed for use in whole farm small watershed managements. It's very similar and actually built on the EPIC model. It's designed to evaluate various land management strategies, including sustainability, erosion, economics, water supply, water quality, soil quality, plant competition, weather, and pest. Management capabilities include irrigation, drainage, buffer strips, waterways, manure management, fertilizations, many different things. Besides these farm management functions, APEX can also be used to evaluate the effects of climate change, and can be used to design environmentally safe, economic landfills, biomass production systems, many different applications. This model operates on a daily time step and is capable of simulating hundreds of years. And farms and watersheds that are simulated can be subdivided into fields based on soil type, landscape use, landscape position, or any desirable configuration. This and the ability to route subfield results through downstream fields distinguish APEX from EPIC. If you need more information or are interested in applying or using the APEX model, you can follow the link below to get more information. SWOT, the Soil and Water Assessment Tool, is probably the most famous model to come out of the Temple Lab. It's a further continuation of more than 30 years of non-point source modeling. In addition to the Agricultural Research Service and Texas A&M University, several federal agencies have contributed to the growth of the model. It incorporates several features of the previous ARS models, the EPIC and APEX models, as well as several others developed here in Temple. SWOT is a river basin or watershed scale model. It was developed to quantify and predict the impacts of land management practices on water, sediment, and agricultural chemical yields in very large, complex watersheds with varying soils, land use, and management conditions over long periods of time. So basins of several thousand square miles can be studied. And the outputs from EPIC and APEC can be fed into the SWOT model. Watersheds with no monitoring data can also be investigated. So SWOT is a very comprehensive and very useful tool that has wide application. Again, if you'd like more information on SWOT, its theoretical equations and user manuals, they're again available at the link you see there in the slide. For those of you new to modeling, the idea of a computer model might be a bit confusing, but it's actually simple in its basic terms. It's simply a coded equation describing different physical and chemical phenomena and their interactions. For example, the relationship between, let's say, rainfall and runoff. This conceptual model diagram of the APEX model shows the different inputs there at the top that the model accepts from topography, soil types, weather, different management practices. The input data are input in the form of text files. The APEX code itself is written in the Fortran computer language, and it consists of hundreds or even thousands of lines of code describing these different equations for these different processes. This is what an actual computer model looks like when you're working with it on a daily basis. The image on the left there is a screen capture of a directory or folder on my personal computer, and it contains a number of files. The two you see circled there, the one at the top, that's the APEX 1501. That's the actual Fortran program that calls all of the other files you see there as text files for input or output. The second one you see circled, the APXV, that is the APEX editor, which is an Excel spreadsheet that's been designed to help users edit each of the different required text files for the model. Here we see in the back the Excel APEX editor open, and it has open a soil file, so a user can then go in and input all the different characteristics of the soil for the area that they happen to be working in. The editor is convenient in that it shows all of the different descriptions of what the different soil parameters are, and then once those are entered by the user from whatever data source they can locate, the APEX editor then will generate the file you see there in the forefront. And that's simply a text file with a .sol describing soils. And you'll notice that it has a specified number of rows and columns that are important for the actual Fortran code that the Apex program will call. And this is the result. After gathering all the information from various sources, formatting them using the editor in specific text files, then running that information through the Apex code, we get an output file. That's what you see here in the back. This is simply a text file. You'll notice it's quite large. It has over 18,000 lines there. So the user then has to go through this output file and determine the information of interest for the particular study that you're looking at. We simply copy that information and paste it over into a spreadsheet where we can further evaluate it. In this case, we've created some charts from the model output. We'll talk about this in the following examples. In our first example, we used the EPIC model to look at some urban irrigation scenarios. We had a student intern who did this problem. She looked at Bermuda grass lawns in a residential community. We did, through literature search, found that irrigating lawns can be often more than half of the total water used by a home. So optimizing irrigation strategies can help homeowners reduce irrigation costs, as well as help city planners design infrastructure and forecast different needs like that. What the student did, she gathered information to build an EPIC model. So she got information on the weather, the slopes, the type of turf, and the different soil types for an area right here in Temple, and put all those files together like you saw in the previous slides, and we ran the EPIC model on that information. And here are our results. In comparing these two irrigation strategies, one schedule-based or timer, like using so much water per week, versus sensor-based, more demand type, looking at soil moisture, we found that both irrigation practices showed an increase in water stress as water application decreased. Let's see that in the top two figures. And more water stress was observed for the schedule-based irrigation than the sensor-based irrigation, also shown in the top two slides there. The schedule-based irrigation used less water than sensor-based irrigation. Well, we can see that in the bottom left slide. And in the bottom right, the final slide down there shows that the biomass and water applied most closely resemble published values for both biomass production and water use requirements. So based on these results, irrigating 1 inch of rainfall every 14 days appeared to be most effective for Bermuda grass lawn maintenance and water conservation in this area. This was a little bit unexpected, because we thought sensor-based demand type might be more efficient, but we speculate that these results were due to overwatering, i.e. saturated conditions, and poor growth, which could explain the lower biomass for sensor-based scenarios. In our next example, we used the SWOT model to look at watershed scale erosion. We collected measured data. We measured the precipitation, stream discharge, and suspended sediment amounts over a period of about 18 months, and took that data and built a SWOT model looking at the stream flow and sediment values. So we built the model and calibrated it based on the field data. The watershed we looked at was named Sesame Creek, and so the Sesame Creek model that we developed for the study is spatially very highly refined from normal watershed models used in water quality studies. We needed this high resolution to properly capture the large range of land slopes, up to 68% in some cases, and the complex urban land use across this watershed. We evaluated 2 different time intervals, a daily interval and a 15-minute time step. And we found that the 15-minute time step provided accurate simulation results and captured sub-daily storm events better than a daily time step model. You can see the different types of data input that were collected for this model shown here on this slide. Well, the first thing we were looking to determine from this Sesame Creek model was is the sediment delivery to the river due to upland erosion or channel bed erosion? So the ability to identify different sources of sediment draining to the river, it was important to develop the protection plan for the watershed. So we evaluated where the soil erosion occurred between overland on the landscape and the channel flow in the creek. Our results showed that 80% came from channel bank erosion and only 20% from landscape soil erosion. We suspect that the cause for this is the high impervious cover. So if you look down there at the bottom left, you'll see that in purple, the purple one, the gray areas are impervious surfaces, parking lots, landscapes. So a large majority of the watershed is impervious surfaces. Would a detention pond effectively help reduce the sediment yield going to the river? The model here suggested that the detention pond in a tributary could reduce peak flow rates by 70% and reduce the sediment suspension that's entrained. The example here demonstrates a significant attenuation of the peak flow on day 86 and 87 in 2018 when we did this study. And the result also showed that the detention pond could reduce sediment delivery by up to 14%. So using the model for testing scenarios, playing like what if scenarios can be very helpful. The last example I'd like to show you today is an Apex model that we built to look at the hydrology and rice production in Japanese cascading rice fields. And much of the data required to build this model were provided by Dr. Samora, and we thank him very much for that. So the basic problem in Japan there and other parts of the world that have cascading paddy fields, they represent up to 8% of rice production, at least in Japan. And rice cultivation stresses water resources in a number of ways, mostly in terms of water usage and then downstream water pollution. So efficiently managing the water use in these systems is needed to help sustain production and conserve environmental resources. So we use the Apex model to evaluate different management and land use impacts at the farm scale. We developed hydraulic routing and management routines that represent terraced rice paddies. And we looked at water use, crop yield, nutrient exports, and sediment exports under different management scenarios. This is the different information and data that was collected to help build this model. The study area, weather, we downloaded that from NASA Global Climate Forecast Reanalysis System information. That's basically the precipitation, temperature, things of that nature. The study area topography, rice fields there in Misaki Town and Okayama. All of that information came from Dr. Samora. Area sizes, slopes, types of soils, and the rice crop being grown, and the practices being used for cultivation there. We came up with two different scenarios, a constantly flooded scenario and a cycled flooded scenario, and then looked at the water use and production. And here are the results from this simulation. We found that constant flooding irrigation at the 50 millimeter level produced the highest grain yield with lowest water use. But constant flooding, however, consistently exhibited more sediment loss than cycle flooding and can contribute to downstream water pollution. Cycle flooding consistently also showed the least amount of nitrogen export, which can help reduce downstream nutrient pollutions. So determining which irrigation type and amount is, quote, best, unquote, depends really on local issues and goals. So something I need to point out is that these results are from an uncalibrated APEX model and may not accurately reflect real-world conditions. So we need field data to calibrate and validate the model. But this again is how models can be used to ask questions, play what-if scenarios, and gain insight for future management and understanding of different processes. Well, that concludes my presentation. I hope you found what I had to tell you about Texas A&M University, Texas A&M AgriLife Research, the Blackland Research and Extension Center, and the models developed here in Temple to be informative and interesting. I hope they may have some application to your own science. I'd also like to thank Dr. Mori and Dr. Samora for the opportunity to participate in today's symposium. If any of you ever have the opportunity to visit Texas, please come see us. We look forward to that. You're always welcome. Arigatou gozaimasu and konnichiwa.